Everyone, this is the first lecture in a mini series about group theory. So here's lesson 1. What is a group? Before we answer that, we first need a definition. So a binary operation on a set X. This is simply just a function. Usually we call it star, from x cross x to x. That's all it is. So we say that star is closed. And this is, we say this because we think of star, we take two elements of x, g and h, and we combine them together to get a new element, which we usually call G star H. And G star H, remember, this is an element of X. So we usually write the function like this. This is the notation. The operation takes two elements of X and gives us one element of X. So now we can say what a group is. It's a set X, sorry, a set G for group, along with the binary operation. Star. And it satisfies these three properties. 1. There exists an element E in G, such that for all G in G, this happens. G star E is equal to E star G, which is equal to G. Usually in a group, the ordering here matters. And we have to write the different ordering. G comes first, and then and E comes first, and then G. These are not always the same, but when it comes to this element, which we call the identity element, we can switch the ordering in which we apply the operation, or in which we combine elements. That's the first property. The second property groups must satisfy. For any element G in G, there exists another element H in G, such that this happens. If I take G and I combine it with H, this is the same as taking H and combining it with G, and then I get the identity element. So for every element in G, I can find some element H that does this. Here we say that H is the inverse of G. And we usually write H is equal to G inverse. Again, this is the notation. Property 3, for all elements G, H, and K in G, we have that if I take G and combine it with this element H star K, remember that H star K, this is the element of G. So I'm still just taking one element of G and applying it to another, or combining them with the operation. Then this is the same as if I had taken this element. If I take this element, G star H, and then combine it with K, I get the same result. And remember, G star H is also an element of G. This property is called associativity. So these are the three properties that a group must satisfy. Remember, it's a set with a binary operation star. But these three properties have to hold. There has to be an identity element. For each element, there has to be an inverse element. And you have to have associativity. Now there's a fourth thing that groups may possess. They don't always have to, though. So for all pairs G and H and G, if this happens, G star H is equal to H star G. In other words, the order I combine these two elements doesn't matter. I get the same thing. And this has to happen for every pair of elements in G. Then we say that G is abelian. But again, this doesn't happen in general. And we'll see some examples of groups where this property fails. But for now, let's look at a simple example. Consider the integers. This is just the positive and negative whole numbers. Along with the operation addition. Then property 1, for all integers in Z, there exists an element such that k plus n is equal to n. And this element k is none other than 0. Whenever you add 0 to an integer, you just get back that integer. So property 1 is satisfied. For property 2, if I have an integer n, then there exists an integer k such that k plus n is equal to the identity element 0. And this k is negative n. So condition 2 is satisfied. 3, it's obvious that if I take an integer n and then add to it some integer k plus m, the quantity k plus n, this is the same thing as taking the quantity n plus k and adding m to it. So condition 3 is satisfied. Therefore, G with addition, or sorry, Z with addition is a group. But further, we know, well, that's not how you spell it. So we know that for any integers m and n, if I take n and I add m, this is the same thing as taking m and adding n. So in fact, Z with addition is abelian. The elements commute with each other. Here's a non-example. So consider the real numbers with multiplication. Well, property 1, there exists an element, namely 1 in R. such that for all x in R, 1 times x is equal to x. So condition 1 is satisfied. For any xyz, if I take the quantity x times y and then combine that with z under multiplication, I get the same thing as if I had taken x and combined that with y combined with z, the quantity. So property 3 is satisfied. Where we get into trouble is property 2. Think to yourself, is it true that for all x in the real numbers, there exists an element y such that x times y is equal to 1, the identity element? So, what if x is equal to 0? Then we have that this element y that we're assuming exists is equal to 1 over x, which is equal to 1 over 0, which is bad. So property 3 fails. So R under multiplication is not a group. So this is an example of something that fails to be a group. And that's because property 2 fails. We don't always have inverses. But we can adjust this. Consider the set R cross, which is just the real numbers take away 0 under multiplication. Then as an exercise, this is a group. So by taking away 0, this becomes a group. Okay, so we've defined what a group is. We've seen a few examples. In the next lecture, we'll go over a few more examples and then we'll talk about properties of groups.